Today we are going to continue our discussion about the EM waves. Before we start, I would like to share a verses in the Bible with you. It is in the book of the Psalm 28 verses 7. The Lord is my strength and my shield. In him my heart trusted, and I am helped. My heart exalts, and with my song I give thanks to him. I know that in the past 1 week during this kind of transition period of time, it's not easy for every one of you, including me. So you definitely have to spend a lot of time adapting using the new approach to taking the courses. Also, we know that most of us probably already stayed at home for almost 1 week. So this is definitely a very difficult time for every one of us. But still, we should trust in God and give thanks to God, even especially at this period of time. And we should also pray for each other. And also pray for the country and pray for the people who lost their job on this kind of difficulty time. And still with the faith in God and believe that the God will guide us and teach us what to do and how to do. So let's rejoice in the God and pray to God, praise to the God. So today we are going to study the energy and the momentum carried by the EM waves. So this is related to the knowledge you learned in the previous chapters. And then we are going to study about the concept of the polarization of the EM wave. So first, let's try to review what we have learned in the previous slides. In the previous lecture, we learned that the speed of the EM wave, no matter what kind of frequency they all have the same speed. And the speed is actually the speed of light, which is c equal to 3 times 10 to the power 8. And most important thing is that the speed of light is independent of the motion of the source or the observer. So no matter who is detecting the wave, the wave of light, they all will get to the same conclusion that they all propagate in a vacuum with the same value. And also we learned that the EM wave is nothing but just a combination of the electric field and the B field. And when the EM wave propagate in the space, for example, along these directions, the electric field will oscillate. So it is not a constant field. So when the electric field oscillates, they will produce a wave which is perpendicular to the direction of the wave propagation. Simultaneously, they also will have the B field induced simultaneously also oscillate perpendicular to the direction of the wave and also to the direction of the electric field. And because of this property, we know that the EM wave is nothing but just the transverse wave. And the direction of electric field and B field and the wave propagation are all perpendicular to each other. So we have studied in the previous lecture how to use the so-called right-hand rule to determine the directions. So for example, if you are given the direction of the electric field and magnetic field, then you should point your 4 fingers of the right hand and curl the finger toward to the direction of B field, and the thumb will be the direction of the wave. So this is a very important thing to keep in mind. And finally, we make a very strong argument or conclusion. That is, if there is a charged particle moving and acceleration in the space, no matter what kind of the charge carried by the particle, they all produce EM waves. So they will propagate in the space at the same speed. So now let's have the first conceptual quiz today. So now if you have a distant star and moving away from the Earth, then the speed of the light from the star will increase, decrease, or unchanged when you try to observe that. So the answer is unchanged. So this is the most intrinsic difference of the EM wave compared with other wave. That is, the Doppler effect apply. They will change the frequency you observe, the wavelengths you observe, but the speed of wave observed is always the same, no matter they are approaching or leaving away from you. So this is a very crucial fact. Now let's try to study the first topic today, the energy carried by the EM waves. So we know that if you have the electric field oscillating, what does it mean? It means that it is actually the movement of the charge. Yeah. So think about the antenna example I gave you last time. So if the charged particle is moving and especially accelerating, then for sure there should be an energy provided and given. And we learned that in the previous chapters that if you have an electric field, then the energy carried by the electric field, the energy density carried by the electric field is expressed in terms of this. So remember, this is the energy density, and this is the permittivity in vacuum. And electric field here in the past, we usually simply treat them as a constant. But this electric field doesn't have to be a constant. It just could be at the particular moment how strong the electric field is. And also, in the chapters discussing about the magnetic field, we know that if you have the electric field, there is also an energy stored in the field. And the energy density stored in the magnetic field is actually very similar to this formula. Instead, it is 1/2 multiplied by the permittivities of the field in the vacuum and multiplied by the B field. So do you remember that the trick try to use the formula, the result from the electric field, and apply to the B field is that every time when you see the epsilon naught, if the epsilon naught is in the numerator, then the mu naught will be in the denominator. They always appears in the opposite direction, position in the formula. So therefore, at the particular moment, if you both have the electric field and magnetic field, which is a EM wave, then the total energy density carried by the EM waves is the U and the summation of the electric field energy density and the magnetic field energy density. So you have to sum them together. So this is the energy density carried by the EM wave. So therefore, now the energy density can be shown in terms of this formula, so-called the electric field RMS. What does that mean? So the formula in the previous slide, the electric field is true for a particular moment, but we know that the electric field is oscillating and the B field is also oscillating. So therefore, at a different particular moment within one period, the value of the electric field could be E1, E2, E3 plus En. So the way how you calculate the average energy density of the EM wave is that you should not simply use the electric field for a particular moment of time. Instead, you should try to get the average value. But now, the average value you are going to calculate is not the one we used before. Instead, the concept of the average value you should use, because the square here, you should use the root mean square. So now, for each of the energy density term, you have the E square. So you simply sum all the E square together and divide it by the number of terms and take the square root. So this is the most general way to define the so-called average value for a quantity which oscillate and change. And in the future, we will simply call this is the root mean square as a RMS. So now you should calculate the ERMS and BRMS instead. And people find out that actually when you try to calculate this RMS value, intrinsically this value will be the same as this value. So therefore, when you sum the two terms together, they will either equal to epsilon naught E RMS squared or 1 over mu naught B RMS squared. So, which means this term and this term are the same. So, no matter which format you use, you can calculate the average energy density of EM wave. So that's the reason I say that the energy density in the electric and the magnetic field are equal. When I say equal, it means that it depends on the root mean square. So if these two values are the same, then we can simply rewrite the formula. So now the electric field can be related to the B field, multiplied by these terms of the coefficient. And if you still remember the result from our previous lectures, this term actually is nothing but just the definition of the speed of light. So what does that mean? It means that when you have an electric field which is oscillating, you will definitely generate a B field. They are always together. And also, they are not independent from each other. So the electric field and B field within EM waves has a connection, and the connection is this. So which means that the electric field is equivalent to the speed of light multiplied by the B field. So therefore, the EM wave not only have both the electric and the magnetic field, also there's a relation between them. And now this is the most common formula and result people will use, which is the electric field divided by the B field is equal to the speed of light. And this is a very important fact, and this is true for all the EM waves. So now let's try to take a look about the second conceptual quiz today. So if you have the magnetic field in an electromagnetic field, and now this magnetic field is doubled, then what happens to the electric field? So the answer will be B, because that for all the EM waves, electric field and B field are connected through this relation. And since you double the electric field, which means that the B field definitely also will be doubled. So this is the very important result.